Hey, good afternoon, everyone. Welcome to the 7th webinar of the IMath Webinar series for this semester. I am Gino Angelo Velasco, and I'm the coordinator for research of the Institute of Mathematics. So first, before we start, I would like to remind everyone that this webinar is being recorded and it is being streamed live on YouTube, and the link is posted on the official Institute of Mathematics Facebook page. Okay, so for this webinar, we'll be having two speakers, one from the Optimization and Approximation Academic Group and the other from the Mathematical Finance and Actuarial Science Group. Okay, so let us introduce our first speaker. Our first speaker is Dr. Arian Cristal T. Velasco of the Optimization and Approximation Academic Group. And today she will present her work titled Sensitivity Analysis of the Complete Electrode Model for Electrical Impedance Tomography. So let us all welcome Dr. Arian Velasco.
Thank you, Sir Gino, for the introduction. Let me share my presentation. Yeah. Okay. Okay, let me start with my presentation. So today, good afternoon, everyone. Today, I will be presenting a part of my PhD dissertation, which is on the sensitivity analysis of the complete electrode model for electrical impedance tomography. And this is under the supervision of Dr. Marian Darbas and Dr. Rainier Mendoza. So here's the outline of my presentation. I first introduced our problem, the electrical impedance tomography, or EIT, and we then proceed to the first part in solving EIT, which is the forward problem. This is where we gather our data for the main problem of EIT, and because of that, we are interested in doing the sensitivity analysis of the potential measurements with respect to the parameters, the conductivity and the contact impedance of the electrodes. In the last part, I will be presenting preliminary numerical implementation, confirming the observations for the numerical sensitivity analysis. So electrical impedance tomography, or EIT, is a non-invasive, radiation-free imaging technique where we reconstruct the conductivity distribution in the interior of an object using electric currents. So in the photo here, we have a patient where there is a belt of electrodes wrapped around its body. So at those electrodes, we will inject current measures, and where we will also record voltage measurement. Using those voltage measurements, we reconstruct the conductivity distributions, which is the image here that we see in the monitor. So EIT, as an active research area, has wide-ranging applications in medical imaging, geophysics, and industrial processes. So in medical imaging, it can detect breast cancer, get an image of gastric emptying, monitor pulmonary, brain, and cardiovascular functions. Actually, the main application of EIT in medical imaging is lung monitoring, because EIT is non-invasive, uh, low cost, and portable imaging technique. In physics, we have fault investigation and non-destructive testing for industrial processes. So in an EIT experiment, we have a finite number of electrodes attached on the surface of the object under test. So we have these blue line segments here. This picture, these are our electrodes, and at these electrodes we inject the alternating currents at a frequency of 10 to 100 kilohertz. And on the same electrodes, we record the corresponding voltages. Using those voltage measurements, we aim to reconstruct the conductivity distribution inside the object. In particular, in this example, we aim to find subdomains omega 1 and omega 2 and their respective conductivity distribution, conductivity value sigma 1 and sigma 2. The conductivity, the background conductivity, so the conductivity inside omega 3 here is usually known. So as I have mentioned earlier, solving EIT is divided into two parts. The first part is the forward problem, and the second part is, which is the main part, the inverse problem. In the forward problem, we aim to find the electric potential given a fixed conductivity distribution and upon injecting a current density pattern at surface electrodes. So you see, this is where the data acquisition is done. And using that data, which are given by the boundary voltages, we aim to recover the conductivity distribution in the main part of the EIT, the inverse problem. So we first focus on the forward problem of EIT. We derive the main elliptic, the governing equation for the EIT experiment. So we first uh, denote omega, a bounded simply connected domain in two and three dimensional space with a smooth boundary. Uh, Sigma is the conductivity distribution of the body, and the scalar electric potential U is denoted by U. EIT experiments usually works at low frequency range. That's why in the quasi-static approximation of Maxwell's equation, we can neglect the time derivatives. So we now have the curl of the electric field E here to be zero, which implies that E can be derived from the scalar potential U, and the curl of the magnetic field H to be equal to the current density J. And by Ohm's law, we have sigma times E. Getting the divergence of this curl, we have the main elliptic equation for EIT. The divergence of sigma times gradient of U is equal to 0 in our domain omega. We then define the boundary conditions with this PDE. So we have the following assumptions first for the boundary conditions. We denote EL, the disjoint contact electrodes on the boundary. Big L here is the number of electrodes, and the set of admissible values of the conductivity to be sigmas in L infinity of omega, where it is bounded below and above by the constants sigma mean and sigma max. We also define the thin, highly resistive layer on the electrode's interface due to an electrochemical effect as the contact impedance. And the set of admissible values of the contact impedance is the set of vector, which has elements that are bounded below and above by Z mean and Z max. I here, the current measure I is called a current pattern if it satisfies the conservation of charge. So the current measures across, the sum of the current measures across all electrodes is equal to 0. So with these assumptions, we now define the complete, or we introduce the complete electrode model for the boundary conditions of our PDE. Okay, so we have these three assumptions, and we note that the complete electrode model is the commonly used and most accurate model for EIT. So the first assumption is that we have the current density on an electrode is equal to the injected current I of L, and that there is no current on the part of the boundary when there is no electrode. So we have zero current on this part here of the boundary. And the last assumption is what separates CM from other models for EIT is we assume that the metal electrodes are perfect conductors, which implies that the boundary voltages are constant, and that we account the voltage drop due to the contact impedance. So this term here is the voltage drop due to the contact impedance. So we have these three boundary conditions for EIT. So this is the CEM forward model proposed in the paper of Somersalu and other authors in 1992. We fix a conductivity sigma, a contact impedance vector Z, and a current pattern I, and we aim to find the potentials, pair of potentials small u, big U, satisfying the elliptic equation with the three boundary conditions. And again, we note that the data for the reconstruction, the data that we need for the reconstruction is the vector of voltage U. Okay, for the existence and uniqueness of solution of the CM forward model, we assume the conservation of charge and we impose a choice of ground voltages. So we have here the sum of the boundary voltages across all electrodes is equal to 0. We define these spaces, so for convenience, we have here the set of vectors satisfying the choice of ground voltages, and now our solution space is given by this direct sum h1 of omega and this space here. Okay, so in the paper, again, the paper of of Somersalu and other authors in 1992, they proved the equivalence of a weak solution to the CM forward problem and the solution of this variational formulation. So we just need to prove the existence and uniqueness of a solution to this variational problem, and in which they used the Lax-Milgram lemma. So here they prove that in the paper they prove that the bilinear form B here given by this integral is coercive and continuous, and obviously this one is linear and continuous. So we now have the existence and uniqueness of solution of the CM forward problem. We now proceed to the numerical solution of finding the numerical solution of the forward problem. So we discretize the variational formulation using finite element method. So we have a triangulation of Lagrange finite elements of type P1. Big N here is the number of nodes. The set of basis functions are var p's of n. And we define a particular set of vectors, phi k's here. And these vectors are used to get a new representation of the boundary voltages. So we have the linear combination of the vectors of the vectors phi k. So this new representation is used to impose the choice of ground potential. This is suggested by Capio and other authors in their paper in 2000. And so now we have the discrete variational formulation. So we have this equation as the discrete variational formulation, and we aim to find the set of this vector containing the nodal values, approximate nodal values of U. And beta here is contains the linear combination constants for the boundary voltages. So discretizing this variational formulation and also the boundary conditions, we now have an equivalent n plus L minus 1 linear system. So we just need to solve this linear system to solve the CM forward problem. So S, M, and C here are matrices with elements given by these integrals. And take note here for G, the absolute value of E1 or EL is just the length or the length for 2D or the area for 3D of the electrodes. P here is the matrix containing with phi k's as columns. So to solve this linear system, we used a direct solver in FreeFEM++. And FreeFEM++ is actually a programming language that is focused on solving PDEs, partial differential equations, using finite element method. So, Okay, now for our numerical simulation, we consider three cases. The first case is the homogeneous case. It is a unit disk with background conductivity sigma 0 equal to 0.33 Siemens per meter. And we also consider a case where there is a perturbation, an elliptical inclusion of the conductivity 1 Siemens per meter. So the second column here shows the corresponding potential or forward problem solutions for these two case domains. And I don't know if you can see it here. There is a faint hint of the ellipse, the perturbation, the conductivity in this part here and the forward solution. So actually, if we get the difference between this unperturbed solution and this perturbed solution, we have this photo here in the third column, and we observe that there is a significant change in the electric potential near the inclusion. So around the inclusion or around the perturbation, and at the electrodes near the inclusion. We will use this as a motivation for the we actually this motivates us actually to do the sensitivity analysis later on. For the second domain, we have a head model represented by three concentric rings. So the outermost ring is the skull, which has conductivity 0.33 Siemens per meter. The blue ring here is the skull, which has very low conductivity, 0.004. And the innermost ring is the brain with conductivity equal to the skull, 0.33. We again consider a perturbation. Now it's a disk inclusion of conductivity 1 Siemens per meter. Again, the second column has the uh, a forward problem solution and getting the difference between the two. So this is the perturbed electric potential. And we observe again significant change in the electric potential around the perturbation. But here you see that there is little to no significant change at the boundary voltages at the electrodes near the inclusion. We can attribute that behavior to the resistivity, to very low conductivity of the skull. In fact, we can say that the skull with a very small conductivity plays a role in retaining the information needed for the EIT inversion, because there is almost no change in the electric potential even if we perturb the conductivity in this domain. The last case is the thorax, which is we get a CT scan of a thorax in this paper of Venkatratnam, and choose we, uh, we, we choose the background conductivity to be 0.67. This is the conductivity of the blood, and the heart's conductivity is given by zero point 0.4 Siemens per meter, and lungs has 0.09. Again, another disinclusion, and we observe the same result as that of the homogeneous case. A higher significant change around the perturbation and at the electrodes near the perturbation. So from this one, if we compare the perturbed and unperturbed potentials, it gives us an idea on which surface electrodes is the electric potential the most affected. So since we have, in the forward problem, this is where we gather the data, we want to check which electrodes contain the most information that will be useful in the EIT inversion. And for that, we study the sensitivity analysis of the EIT measurements. So sensitivity analysis is the study of how the input perturbations of a mathematical model influence the variability of its output. So in our case, since we generate the data in the forward problem, we want to study the behavior of the forward solution, which is the potential, which are the potential measurements, when there is a slight variation of physical parameters, such as the conductivity or the contact impedance on the electrodes. And we introduce the Gateau differentiability as a mathematical tool for the sensitivity analysis. So if we have a directional, if the directional derivative of W of P in the direction mu exist for any direction mu, and that the map from the direction mu to the directional derivative is linear continuous, then W is said to be Gateau differentiable at P. In the next section, we will prove that the potential, the electric potential, or the pair of solution for the forward problem is Gateau differentiable with respect to the conductivity sigma and contact impedance vector z. So sensitivity with respect to the conductivity, consider the unperturbed and perturbed variational problems. So here, we let the solution to the original problem, the pair small u, big U, and B sigma here is just equivalent to our bilinear form we defined earlier. For the for the perturb problem, we have a perturbation sigma plus h mu, which is still in the set of admissible values, and the direction mu is in L infinity of omega with norm equal to 1. The solution of this perturb problem is denoted by small uh, big UH, and we highlight this part here is just this is the difference between the two variational problems. We denote the Gateau derivatives to be small u1, big U1. So this proposition actually it states that the solution of the forward CM forward problem is Gateau differentiable with respect to the conductivity sigma, and the Gateau derivative is actually the unique solution of this variational problem. So we just need to prove the existence and uniqueness of solution of this variational problem, where we will use again Lax-Milgram lemma. And since B sigma here is equivalent to the bilinear form we defined earlier, for CVT and continuity follows, and the right hand side is obviously linear in mu, and it's also continuous. So from this one, we can now approximate the Gateau derivative by solving this variational formulation. And again, using the finite element method to discretize this variational formulation, we have the following numerical implementations. So our setup is we attach 32 electrodes. The current pattern is this sine function here, and the contact impedance is constant across all electrodes, and we get the direction of the perturbation, the characteristic functions on a disk D. So this is for the unit disk, and these are the electrodes for the thorax. Okay, so for the homogeneous case, we consider three cases of perturbation. So we have a perturbation near the center. This one is near the boundary, and this one it has larger size of perturbation. And again, we observe higher sensitivity values around the perturbation. And if the perturbation is near the boundary voltages at the electrodes near the inclusion has also relatively larger sensitivity values. And if we have larger perturbation, we get relatively larger sensitivity values, and has the most, also the number of electrodes affected by the perturbation also increased. For the head model, we have the same representation, three concentric rings, and this is the perturbation near the center. This one is near the boundary, and we get actually relatively, comparing to that of the homogeneous case, we get relatively smaller sensitivity values here. And again, we have here, even if the perturbation is near the boundary voltages near at the electrodes near the inclusion is almost unaffected. So we can attribute that again to the resistivity of the skull, which is in this case, if we only perturb the skull's conductivity, we get really large sensitivity values. And this confirms that our EIT measurements are highly sensitive to uncertainties in the skull's conductivity value. For the thorax, so this I will just point out, this perturbation is near electrodes 20th and 22nd electrodes. That's why we get relatively larger sensitivity values comparing to the other two. And also this one, this perturbation is close to the 27th one, and actually we get relatively larger sensitivity values comparing to the other three electrodes. So we observe the same conclusion here that the the electric potential is more sensitive near the inclusion, and at the boundary voltages if the electrodes is near the inclusion, right? Okay, so for the sensitivity with respect to the contact impedance, we again observe the two problems, the unperturbed one and perturbed one. So this is still the same as B sigma. I used different notation. So here, unperturbed conductive contact impedance. And we for the perturbed contact impedance, Z plus eta H. So our direction is eta. We let U tilde H, small and big U tilde H, to be the solution of the perturbed variational problem. So the difference between the two is this part here. Okay? And then the Gato derivatives is denoted by small u2 and big u2. So this proposition assures us of the Gato differentiability of the electric potential with respect to the contact impedance vector Z. And it's the Gato derivative is the unique solution of this variational formulation. The existence and uniqueness of the solution here follows the Lax-Milgram lemma. And the highlight actually of the proof of this proposition is the use of the Taylor expansion for the perturbed contact impedance vector. So we use this Taylor expansion to get this variational formulation. So for the numerical sensitivity, we consider two cases. One is one in 2D and one in 3D, a unit disc and a unit ball. So uh, for eta, we construct eta by setting it setting eta L to 1 if there is a perturbation of the contact impedance of the Lth electrode, and 0 otherwise. So in here, we perturb the 16th electrode. Okay, the 8th, I think, the 7th electrode. So and we conclude actually that the sensitivity values, the highest amplitude of sensitivity values is localized at the perturbed electrode for both the 2D and 3D case. The 3D simulation here is done by a colleague, Jeremy Ellen. Okay, so actually the numerical sensitivity we've done earlier provides us the information on which surface electrode is the electric potential most affected. So we present here a preliminary numerical implementation that will confirm those observations. Okay, so the inverse conductivity problem for EIT is also known as the Calderon's problem, and it is a nonlinear and highly ill-posed problem. Again, this is where we recover the conductivity distribution using voltage measurements on the electrodes. It was proven by Kohn and Vogelius the identifiability of the conductivity using a full knowledge of the voltage to current map in 1984. And then by Koenig and other authors, they prove it. They prove the identifiability of the conductivity when only partial information of the voltage to current map is known. In practice, actually, we only have partial information of the voltage to current map. And our aim here is to retrieve a finite number n of inclusions of different conductivities in sigma. In particular, we want to approximate vectors p and s, the vector p containing the geometric attributes of the inclusion and s the vector of conductivities, such that the error between the approximate and measured voltages is minimum. So our objective function is this equation here. So this is the approximate voltage, a boundary voltage, and this is the observed or measured boundary voltage. For the preliminary numerical implementation, actually, we set the geometry to be fixed. So we only want to determine the vector of conductivities S. Our setup again, the same, 32 electrodes, constant contact impedance 0.1, and we use 16 current patterns. So we just rotate the first current pattern. So the first current pattern is given by this formula here, and we just rotate uh, the first current pattern to get the next 15 current patterns. Okay, so if we use 16 current patterns, we actually have a 16 voltage data measurements, and we add 1% random noise to the voltage data to model experimental errors. The forward problem is solved using FreeFEM with different mesh size for the data generation and the inversion to avoid inverse crime. And the inverse problem is solved in MATLAB using the built-in command for VFGS algorithm fmina. The tolerance is said to be the default value e to the minus 6. So we work with a synthetic data where we generate, that are generated setting the background conductivity to be 0.33 Siemens per meter and a conductivity 0.4. So this is the homogeneous case. The forward and inverse mesh has the following characteristic. So we used different mesh sizes. And the only unknown variable in this case is the conductivity inside the inclusion sigma p. The initial guess is said to be 0.6 Siemens per meter. We consider three setups to confirm our observations from the numerical sensitivity. So in setup A, we use all the voltage measurements on all the electrodes. In setup B, we only use 16 voltage measurements, and these are located on the electrodes on the side of the inclusion. So this part here. So since the inclusion is on this part, we are assuming that these electrodes contain the most information needed for the inversion. And setup C is on the opposite side of the inclusion. So these contain little to no information needed for the inversion. For setups D and E, we perturb the contact impedance on these electrodes containing more significant information, and setup E for the electrodes containing little to no information. So here is our estimated conductivity distributions. So setup A and B, this is our true solution. Setup A and B here actually doesn't have any, it's not obvious. Their difference is not it's not obvious as compared to that of setup C, which is uh, this confirms our observation earlier about from the numerical sensitivity with respect to the conductivity, that the useful information needed is at the electrodes near the inclusion. And if we use the voltage measurements on the side on the electrodes opposite side of the inclusion, we get a relatively larger, or actually relatively larger error for the approximate solution. Setup D and E also, we cannot see the difference between the two, but if we check with this table here, so we have here the relative error for setup C is very large, because we only use the information on the electrodes with little to no information. And for setups D and E, if we perturb the electrodes on the side of the that contains the most significant information, then we got a higher relative error as compared to that if we perturb the ones with no or little information. And we conclude that accuracy deteriorates when the EIT measurements on the electrodes located on the side of the inclusion are missing. So to summarize, we from the numerical sensitivity, we now know which electrodes contains the most useful information, and those electrodes actually the electrodes close to the perturbations in the conductivity. And for the numerical sensitivity with respect to the contact impedance, it is actually localized on the faulty electrode. This is actually very important because if we have a faulty electrode on the side of the boundary where it is close to the perturbation to the perturbation in the conductivity, then it is more difficult to do the inversion, to do the reconstruction of the conductivity because most of the useful information will be missing. Some perspective from this work is actually that's why we only gave preliminary numerical implementation, because we want to find an explicit relation between the EIT measurement and the geometric parameter. So we want to actually uh, determine an algorithm that will use the numerical sensitivity or the sensitivity that we got for the inversion of EIT. So it could give good initial guesses for an iterative reconstruction process. Also, rigorous sensitivity analysis with respect to the shape of the electrode can be done. This is for irregular shape domains, because in our work we only consider equally spaced electrodes and of equal lengths. Thank you for your attention.
Okay. Thank you very much, Dr. Velasco. Let's give her a round of applause, virtual applause. Okay. So thank you. Do we have any question from the audience? Any question from the audience? Okay. Yes,
Hi, sir.
ma'am, yes, question po. Sino yan? You may speak. Sir Ren, yes.
Hi, si Ren po to, sir.
Hi, good afternoon. Yes, you have a question?
Yes po, sir. Hi, Ariane.
Hi.
So thank you for your presentation. Can you give sort of an application of the sensitivity results in the context of medical application?
Okay. So we are actually thinking about if we know which part is more sensitive or which electrodes is more sensitive. I think it's more useful for the detection of brain tumors or in general tumors in the thorax or in the brain. That's why we had the head model earlier, because we wanted to focus on the most useful information that we will get to do the inversion, to have to do the reconstruction easier. To do the EIT reconstruction. Also, I think for the brain tumors, because if we know which part of the boundary is more sensitive, then we can just focus, or actually we can put lots of electrodes and we can have almost full information on the voltage to current map, which is in practice we don't have. But if we focus on that part only, we can Still, we don't have to use the whole boundary, but we still get an accurate solution.
Okay. Thank you. I have another question. So for those maybe some of the participants are interested in doing numerical PDE. So you've shown like you solve PDE on a irregular shape domain like a thorax, right? So maybe can you give like maybe idea on or preliminary that students are required sort of, no? Para mga skills na kailangan nila kung gusto nilang mag-work sa numerical PDE.
For sa, wait,
Yeah,
sorry.
I think Dr. Mendoza was asking kung ano yung prerequisites na kailangan ng student who would wish to pursue research on numerical PDEs. Is that correct?
Yes po, sir. Yes po, sir. That is Mr. Gabriel.
Usual, kasi mostly the programming language that I use, kasi nga we consider yun nga yung irregular shape domain, so yung thorax, and later on we will consider irregular shape perturbations. So I mostly use FreeFem++. So ito ay computing software developed by French institute, a French institute. And yeah, so usually ang ginagawa ko kasi is yung forward problem ay sinosolve ko using FreeFem, tapos kinocall ko siya sa MATLAB. So medyo kailangan ng skills, kailangan matuto ng FreeFem at ng MATLAB. And yeah, for this particular research. Kasi ang mahirap kasi kaya mas okay sa akin na mag-solve sa FreeFem++ ng nitong ating numerical sensitivity, kasi yung mga mas madaling mag-generate ng triangulation sa kanya compare sa MATLAB. Halos sa MATLAB, ang nakukuha lang natin ay square domains. Kasi mahirap gumawa ng mahirap gumawa ng mesh at mahirap i-implement yung finite element method using that mesh, using MATLAB.
Okay. Thank you. Yan lang po.
Thank you, Dr. Mendoza. So question lang doon sa perspective, I think andito pa siya sa slide mo. No? So doon sa nabanggit mo na center, so part din dito yung position ng inclusion na...
Opo.
Okay.
So
yun na so kung malayo sa border o hindi, tama ba yung... So yung iba't ibang position din, consider niya rin ba?
Opo. So parang ang iniisip po namin, kasi usually ang kinukuha lang po namin na geometry ay ellipse or circle. So para maging general tumor siya, iniisip namin gamitan ng Fourier series, tapos yung yung mga coefficients sa Fourier yung i-estimate po namin. So actually nakagawa naman po kami with na hindi fixed yung geometry, pero using different algorithm for the optimization. Kasi dito po ang ginamit namin ay BFGS, a quasi-Newton method for the optimization.
Tapos yung sa thorax na application, real data ba siya? So nakuha talaga siya from
Opo, sir. Parang ang ginawa po namin ay sa FreeFem po, kasi pwede siyang import ng image. Tapos pag import niya, siya na po yung gagawa nung mismo. Hindi nga lang po namin alam kung ano yung mismong curve nito, pero yun, siya na yung gagawa ng curve and then magta-triangulate na siya. May ginawa pa po kaming isa po na parang in-approximate naman namin siya using yung data. So dalawang way po, either using FreeFem na diretso from the image or using MATLAB na ina-approximate using Fourier series yung boundary, yung curve. Kasi kung may curve na po sa FreeFem, okay, diretso na po yung triangulation.
And sorry, last one. I can't remember if maybe I missed it or ano. Naka-focus lang ba kayo sa convex na shape or pwede siyang ano? Or pwede siyang non-convex? Kasi na-imagine ko baka mag-iba yung ano nun eh. Kapag may part ka na hindi convex tapos may electrode ka doon na nag-aano siya. Tama ba?
Opo,
Magic.
yun po. Kaya po parang pwede din po siya doon po sa perspective na paano po yung shape ng electrode if ever ganun. May nakita po ako, ang focus po namin usually ay yung mga nagawa pa lang po namin, yung mga convex pa lang po. Pero may nakita na po akong paper na nag-study ng as in irregular at non-convex. Tapos, ino-optimize po nila yun using shape derivative, ino-optimize po nila yung shape ng electrodes for it.
Okay, thank you. Do we have any other question for Dr. Velasco? Okay, kung wala na po, let us give her another round of virtual applause. Thank you. Okay, so at this point, actually, unfortunately, our next speaker, Dr. Ramon Marfil, is having connectivity issues because of power outage in his place. So yeah, I think he won't be able to come back today, but we will try to reschedule his talk for next meeting, for next Monday rather. Okay, so that ends our webinar for today. And it was supposed to be the last webinar today. So we will have the last part two of the final webinar for the semester, possibly next Monday. Okay, so thank you very much for attending, and thank you to Dr. Velasco for giving the very nice talk. Okay, so see you possibly next Monday. So please check the official IMath Facebook page for updates. Okay. Thank you. Goodbye.
Thank you, Gino. Thank you, Ariane.